Hello, today we will discuss the Initiated Chemical Vapor Deposition Lab. Our team was comprised of Mary Mohammed, Fawaz Al-Bassam, John Lombardo, and myself. Chemical vapor deposition is a chemical process where a solid film is deposited on a substrate as a result of the reaction of reactants in the vapor phase. This process is used in the production of high-quality and high-performance materials and is a basic tool in manufacturing. It is especially useful since it allows the coating of substrates that are not compatible with other polymerization processes. These substrates may be sensitive to temperature or solvents. The objective of this lab was to explore the effects of stage temperature as well as the ratio of the partial pressures of hexyl acrylate and tert butyl peroxide, TBPO, on the deposition rate. We tested chiller temperatures of 10, 15, and 20 degrees C, and we tested ratios of 4 to 1, 4 to 2, and 4 to 3 hexyl acrylate to TBPO. We will also calculate the activation energy for the polymerization reaction. This lab will draw on knowledge of vapor phase flow, reaction kinetics, mass transfer, and polymer chemistry.
To determine the deposition of the polymer, we must first calculate the angle of refraction of the laser, theta 2. This is determined by the first equation, which calculates the cosine of theta 2 as the square root of 1 minus the sine of theta 1 divided by the index of refraction squared. Theta 1 is defined as the angle of the detector from the substrate.
To calculate the deposition per sinusoidal cycle, we use a second equation. This defines the amount of deposition, i.e. the change in film thickness, to the wavelength of the laser divided by 2 times the index of refraction times the cosine of theta 2. Lambda is the wavelength of the laser, which is 633 nanometers, and the index of refraction is 1.428.
To calculate the activation energy for the reaction, we will use the last two equations. The natural log of the rate is equal to 2 times delta H over RT. In this case, R is equal to 8.314 joules per mole Kelvin, and T is the substrate temperature. We solve for delta H and can then substitute that into the last equation to get the activation energy.
Before starting the experiment, you must first wear the proper protection gear. This includes gloves, goggles, and a lab coat, worn correctly.
Oh hey, didn't see you there. Thanks for stopping by. I'm just cleaning up the setup because, we have to take really good care of this stuff. It's actually $250,000 total setup. That's $250,000. Now, an example, this one pump alone costs $10,000. You know what we could do with that? A lot. There we go. We clean the glass with Kimtech Delicate Task Wipes, the science brand, an industry leader in lab technicians.
This graph plots the inverse temperature with the natural log of the deposition rate. As you can see, a decrease in temperature correlates to an increase in deposition rate. This is likely due to the fact that the reaction is exothermic.
Looking at the values for TBPO plotted against the natural log of the deposition rate, there is an indication that an increase in TBPO leads to an increase in deposition rate. This is due to the fact that TBPO is the initiator for the polymerization reaction. Overall, we calculated the activation energy to be around negative 38 kilojoules per mole. The value from the literature is negative 41 kilojoules per mole. The discrepancy can be due to experimental error. It seems that a decrease in chiller temperature leads to an increase in deposition rate, and an increase in TBPO leads to an increase in the deposition rate. More testing still needs to be done in order to confirm our results.